the next session of embedded software testing. Uh, this is the 19th lecture series of embedded software testing. This part 2 or unit 2. Here we study about the white box testing techniques. Uh, in the previous session, we have understood about some of the basics of dynamic testing in terms of white box and black box. Uh, So we need to have a strategy, test case selection methods, and coverage criteria. These are very important aspects for doing the white box and black box testing. We also studied about the differences between the white box and the black box testing. Basically, black box is a functional or data-driven. It's purely based on the requirements, and the design techniques are also based on the functional behavior of the system without any knowledge of the internal or implementation details of the system under test. Similarly, in the white box testing, the implementation of the code will be studied, and partially the tester will have knowledge on the entire system, but his focus will be purely on the white box design techniques in terms of the structure of the code. Also, there is an intermediate layer called a gray box. It can have a mixture of both white box and black box, where the coverage is not possible with the white box and black box as well. So we can have a credit of both of them, that is called gray box. And code coverage, we know total number of executed code that is tested divided by the total code that is there in the system. So this is called as code coverage in percentage. Similarly, requirements coverage we have. This talks about the total number of tested requirements versus the total number of requirements in percentage. Also, we studied about the black box testing and white box testing differences and their advantages and disadvantages as well. Okay, in continuation of that, today we study about the coverage, the white box testing. What are the types of white box testing? So the broad categories are statement coverage, where all the executable statements in the program we need to test it because they will be executed. So we need to see that they are going to get tested and whether we are able to test it. So we need to have the test cases selected as per the same. The next one is a decision or a branch coverage. Here test cases chosen because every branch, it is called a branch also, the decision. So the decision can lead into a true or false path. So both have to be executed at least once. So that is why it is called a decision coverage or the branch coverage. Similarly, we have a condition coverage. So in this type of broad level coverage, we have test cases choosing to force each condition in a decision to take on all possible logic values. Suppose we have multiple conditions available underneath the test. So we need to exercise all the possible paths that the condition takes. And it could be a logic expression as well. So we'll study about that condition coverage in detail in the coming slides. Okay. So all this together it is called as a structural coverage. So this is a white box uh, testing technique on total. It is called as a structural coverage, which has a statement, decision, condition, modified condition, and there are different types that are underneath this structural coverage. In the end of the structural coverage, we do a technique called structural coverage analysis. So, which is a method which does coverage credit and how much coverage is done and how much coverage is pending. So the end goal is to reach 100%. So that is what the structural coverage analysis is. Altogether, it is called as a structural coverage. You can see a table. This is typically used in industry as part of the coverage is concerned. So you can see different coverages on the right hand side. Statement coverage, decision coverage, condition coverage, condition decision coverage, MCDC, modified conditions decision coverage, and multiple condition coverage. So what are these and how these are covered in different types of coverage criteria? So every point of entry and exit in the program has been invoked at least once. That means we have several program units or the function units. So that function will get entered and the function gets executed after the function is executed. So whatever the possible ways of entering into that function or the procedure and whatever the possible ways of exiting out of that function has to be invoked at least by that program. That sort of a testing is done with the help of decision coverage, condition decision coverage, MCDC, and multiple condition coverage. These are responsible because there are the function could have conditions, decisions, modified conditions, etc. to make sure that all the entry and exit criteria have been taken care. Okay. The next one is the program will have statements. All the statements need to be touched once. All the statements need to be invoked with the help of that testing method. So this testing method is called statement coverage. The next one is every decision in the program has taken all possible outcomes at least once. That means we have a diamond box, decision box. We can draw it how it looks. So we have a decision box. It will be having certain conditions. So the decision can take as true or it can take as false. This path can take as yes or no, yes true, no false. So likewise, all the decisions in terms of covering this path. So these decisions have to be invoked. These decisions have to be covered. So those type of testing are covered in the decision coverage, condition decision coverage, MCDC, multiple condition coverage. The next one is every condition in a decision in the program has taken all possible outcomes at least once. That means the conditions that has come out in the decision should have taken whatever the possible outcomes that it yields. So that will be taken in the condition coverage explicitly along with the condition decision because we know that decision is also there involved. So the condition coverage, every condition in addition in the program has taken all possible outcomes at least once it has to be exercised. The next one is every condition in addition has been shown to an independently affect that decision's outcome. That means that whatever the execution path that we have should be independently covered. It means the preconditions that is required should be independent. So that will be done with the help of MCDC. This MCDC, otherwise it is called as modified conditions decision coverage, decision condition technique. This is mostly used in aerospace and space industries with the help of a standards called the Devon's energy. I will probably explain that aspect in detail in the future slides. It is called as the Devon's energy standards basically. And this one, along with the multiple condition coverage, we have this decision coverage criteria is met. The last one is every combination of condition outcomes with a decision has been invoked at least once. This is with the multiple condition coverage where the different several conditions, because a program or the function could have similar or different sort of diamond boxes and processing statements. All that parts have to be executed with a several combinations of them. So that is done with the help of multiple condition coverage. So this table talks about the coverage criteria, what are the types of coverages we have. We will study each of them in detail. Okay, so white box testing has the below types of testing methods. The first one is being statement testing, and the next one is branch decision testing. The other one is data flow testing, and branch condition testing. We have branch condition combination testing. We have modified condition testing, and the last one is linear code in sequence and jump testing. Okay. Statement testing, the idea with the statement coverage is to create enough test cases so that every statement in the source code has been executed at least once. And in branch decision testing, the idea with decision coverage, the idea with decision coverage is to execute every single decision in the code at least twice. It means we know that decision can be leading to a dual path, true or false. So both possible outcomes of the decision should be executed in order to reach full decision coverage. That means the decision coverage is being taken care of branch or decision testing. The next one is the data flow testing. Here what we do is the test cases are designed based on variables that are used within the code. Basically, purely this is based on uh, the data. So the data, how it is represented with the help of variables. So all those variables have to be considered in terms of their usage and the flow, what are the values it takes. So that is taken care with the help of data flow testing. The next one is branch condition testing. A test case. This is a test case design technique in which test cases are designed to execute branch condition outcomes. The next one is a test case design technique in which test cases are designed to execute combination of branch condition outcomes. That means we have different combinations of the branches. That is done with the help of branch condition combination testing. The next one is the modified condition testing. Here, in this design technique, test cases are designed to execute branch conditions outcomes that independently affect a decision outcome. That means the independency of that decision will be taken or considered in this modified condition testing. The last one is linear code sequence and jump technique. In this, select test cases based on jump-free sequence of code. That means some codes like interrupts and those things run independently. So this consists of about three type of things: executable statements, the linear sequence end of that it will be there, and the target line to which control flow is transferred at the end of the linear sequence. That means we have the start of the sequence and the end of the sequence and the target line to which the control flow is transferred at the end of the line sequence. So we will study in detail about this type of this. And the last one is one more technique also we will study that is specifically followed in aerospace with the help of D1 standard, that is MCDC. So that also we can consider. Basically, that is having this modified condition decision coverage. That is nothing but the branch condition combination and modified condition. Both together it is called. So we'll study that in detail. Okay, statement coverage. So execute every statement in the code at least once during the test case execution. That means it's basically a fundamental technique that every testing, it doesn't matter embedded, non-embedded, application, Java, whatever you call, all this type of testing, they use this statement coverage. Uh, in this statement coverage, test cases will be created so that every statement in the source code has been executed at least once. So that is the aim of this statement coverage. So basically, they use tools basically such as white box statement coverage testing tools, uh, LDRA, VectorCast, load runner, RTRT. A lot of tools are there specific to the need of that particular industry embedded software. They use this, and the coverage is, as I said in earlier slide, earlier session, the coverage is taken into credit with the help of executed number of statements versus total number of statements. That means suppose with the help of this statement testing, the coverage how we will arrive it. Suppose we have executed total number of lines 89 and the total number of statements that are there. Here statements are nothing but the lines of code, the executable lines of code. This excludes all the comments and everything. So in C, if you consider every semicolon is a executable lines of code. Also, it is called as EOC. So basically, this total number of statements need to be executed in white box statement coverage, but it may not be possible to do 100%. So there are other methods that we will have to do it, like whatever that methods that we have seen, like condition coverage, modified condition coverage, and all that. Because every path needs to be executed by its own technique. So, and the coverage is done with the help of percentage. Here it is 89%. 89% is the statement coverage. So the 11% is the gap. The 11% we need to take care. So the workflow when using the statement coverage is to first execute all existing black box test cases that has been created while monitoring the execution. That means if we have done the black box requirements testing, we can do that if possible with the help of white box and monitor what are the statements that have been executed. Then this monitoring is in all but the simplest test cases performed with the tool support basically, as I said. So when all black box test cases have been executed, the tool can report which parts of the code that remain untested. It means we know that 11% is untested. So now we need to construct new test cases that will cover the remaining statements as much possible. So we will start with the part of the code that should be reached. Walk backward in the code to determine the values of the input variables required to reach the desired part of the code. Then accordingly we will provide the inputs, whatever the values, specific values that are required for that lines of code that are not covered. So how we can feed the inputs with the help of the specification, whatever it is being spoken about, the functionality or the variables, if it is possible. And the expected results also can be drawn out of the specification. So this new test case also will be executed and monitored. And one thing we should take care is we should not expect the result from the code itself. We should go by the specification and the functionality. So of course, the code should complement and not from code. So this is a very important aspect. So we cannot have, because code can have a local variable or uncalculated values or intermediate values. So we may get biased or it may be half cooked. So better to go with the functionality for that unit piece of program what is expected, and accordingly we need to put the expected results and try to see whether it passes or fails. So that is about statement coverage. And as I said, all the statements have to be monitored and executed and tracked. So what will happen is this monitoring technique, or what is that called, um, observation we want to have on the executable statements. It's not possible with the help of manual. If it is say some 10-20 lines, okay, we can do it. But there are big embedded programs having 50,000 lines of code. So what will you do? It's not it's impossible to have a manual inspection of that. So what we need to have, there are test hooks that can be used, something like a printf we can add to see that every statement is executed. The printf will print, suppose printf statement number executed, something like this, statement number. And every lines of code we can have this statement number implemented accordingly. We know that what is that being printed, and if there is a missing thing, so we know that how many statements have been missed. But the problem is here, we cannot have printf done by ourselves every time. So that is why we have a hands-on to cover this. We have a tool called instrumentation. This technique is called instrumentation. What we do is we will provide the monitoring ways of observing how many statements have been executed or what are the statements that are missed. So that report will be done with the help of instrumentation, where the existing lines of code or the code, the program will be instrumented in such a way that the tested part will be reported. So for this instrumentation, there are a lot of tools. We'll study about the tools. So what it does is basically we will feed all the source files, and it will add the instrumentation code into that and execute on the target or the host depending on the nature of the embedded system. There are other challenges that I will speak about that, where we add instrumentation and it will add a lot of lines of code, and the total lines of code will increase. Suppose 50K LOC we have, and the instrumentation is suppose another 20K, it will become 70K, and which may not fit into the target system. So what we can do in that case is we can do a partial instrumentation and take the credit by overlapping all of them. So that is how the instrumentation of statement testing is done. Okay, software instrumentation. Software only measurement methods are all based on some form of execution logging. That means the logging of the execution or the monitoring of the execution is required to do the statement coverage. Okay. The implication is that after the after the block is entered, every statement in the block is executed. By placing a simple trace statement such as printf at the beginning of every basic block, you can track when the block, and by implication all the statements in the block are executed. This is what I explained. So if it is a RTOS, the RTOS itself will provide a logging service. With the help of we can do it, but not all embedded systems will have an RTOS or a facility with RTOS to trace it in terms of the logging the calls or memory in the target system. So we'll use the instrumentation technique with the help of the tools, external tools. So less intrusive form of execution logging might be called low intrusion printf, because it doesn't introduce much into the existing program. A simple memory write is used in the place of printf. At each basic block entry point, the logging function marks a unique spot in the access data memory. After the tests are complete, the external software correlates these marks to the appropriate sections of the code so that the code, whether it is used or not used, will come to know based on the memory aspects. Alternatively, the same kind of logging call can write to a single memory cell, and a logic analyzer is another tool, as I said, for instrumentation and statement coverage. They use it. It could be a hardware interface such as a logic analyzer, which will capture the data from the memory and analyzed. So that is how the software instrumentation is done. And the challenging part or the interesting part is that if the system being tested is ROM based and the ROM capacity is close to the limit, the instrumented code image might not fit. As I said, if there is a 50,000 lines of code is there, and the instrumentation after we are done with that, it could come to something like 75k, and whereas the embedded system has a memory of 75k, definitely it's in the border or it may creep more than that. So what we can do is we can improve your statement coverage by using two or more rigorous coverage techniques. We can improve that by the help of overlapping technique, and statements we can reduce it partially. And the further testing or the statement coverage we can use with the help of decision coverage and MCDC, modified condition decision coverage. So that is how the software instrumentation is done. There are various tools. We will touch base some of the tools as an example at the end of this session or in the next session. Okay. In going in detail of the statement coverage, you can see there is an example provided. To achieve statement coverage, every executable statement in the program is invoked. This once during the software testing, we know that. Achieving statement coverage shows that all code statements are reachable in the context of D1 and B, reachable based on test cases derived from the requirement. Here, they use either a design or the requirements to have that reachability aspects. That is what is spoken in the D1 and B process. It's standard. So, for example, if x is greater than 1 and y equal to 0, then z will become z by x and if. So, this is one statement. So, by choosing x equal to 2, y equal to 0, and z equal to 4 as input to this code segment, every statement is executed at least once. We know that there are two statements. These two statements, how we can go to execute is by providing such values. So it will enter into that then portion only when fx is greater than 1. Here we have chosen x as 2. So definitely it will go inside this, but there is one more condition called AND condition. So this logic expression we need to satisfy by putting y as 0. So when y becomes 0 and x is greater than 1, that is 2. So z will become z by x, and z is provided as 4. So that will become 4 by 2. It's 2. However, if an OR is coded by mistake in the first statement instead of an AND, the test case will not detect a problem. That means we will not be able to detect the issue that is here because the implementation is wrong. So this is some sort of a disadvantage. It goes purely by the test case selection and the code understanding. If the code is wrong, then it may be difficult. So as per one embedded software expert Mayer's, statement coverage criteria is so weak that it generally considered as useless. So at best, statement coverage should be considered a minimal requirement. That means a sort of statement coverage we need to do to have a confidence that the maximum statements have been reached or statements have been invoked. So in that way, basically we can use this statement coverage technique, and rest of them we use the other techniques. Further elaboration of the statement coverage, you can see there are about 5 statements in this program. Here is a program block within the flower bracket. So we have multiple blocks in terms of small flower brackets. First two statements are executed first, then there is a condition. If the condition is fine, then statement 3 and 4 are executed. If the condition is not good, then statement 5 is executed. There are total 5 statements that are to be exercised in this program. How are we going to do it? So because the statement coverage, we need to make sure that 5 statements are invoked at least once. So we need to make sure that the condition we are going to provide such a way that the condition can take both no as well as yes with those values. So by statement coverage, going plainly, we definitely are going to cover first 2 statements, and the second part, it will based on the result of the 2 statements, statement 1 or 2, it will go either as yes path or no path. So either case we will execute only 3 statements or 4 statements. One of these will be exercised. So with this statement coverage approach, at best we can achieve either 3 with the no path or 4 with yes. Statements are exercised. So statement coverage can do this much because the conditions it won't care. So that is how this has been done with the help of 5 statements with the conditions that are underneath this. Okay. When creating test cases for statement coverage, you can make use of control flow graph. So control flow graph is something like how the flow is going to happen. The statement coverage requires statements in the code to be executed. We know that the boxes and the diamonds represent all the statements in the code. So that is also part of the statements. So that that also will be reached with the help of statement coverage. By following the paths through the code, we cover all the diamonds and all the boxes are covered, and thus we have statement coverage. According to the relation with Maccabee, Maccabee is a person's name, but he found out he discovered this standard to measure the complexity of the program based on all these diamonds and processing statements. So according to the relation with the Maccabee measure it is called, there should be 3 or less test cases, and in this case 2 are enough. So to have 2 paths, what I said is we need to have 2 test cases. The first test case will take care of statement 1, 2 and 5. The second test case will take care of statement 1, 2 and 3 and 4. So 2 test cases are enough with this measure. How much of the total executable statements have been hit covered by the various test case scenarios is what is important in terms of statement coverage. For a decision statement, both true and false conditions should be tested, even if the decision statement is of implicit form. Though it is internal, that means it depends on the some of the internal variables or locals, not the external one. That needs to be exercised still. In the given piece of code block, if condition is false, then 3 out of 4 statements are said to be covered. So we know that statement 1, statement 2, statement 5 have been exercised if there is a false condition exists or no condition exists. To achieve 100% decision coverage, both true and false conditions have to be achieved in 2 different test scenarios, even though the statement is of implicit form. So the second form is we need to have another statement coverage with the path taking as yes or true with the help of that statement 1, 2, and 3, 4 have been exercised. So in the first form, we have exercised the first one, and in the second one, we have exercised the true path. It is false or no, whatever you want to call. So that is how the statement coverage in terms of total number of executable statements reaching will be done. Okay, so that is what is about statement coverage. All the executable statements have to be reached. Next type of white box testing is on the branch testing or the decision coverage or decision testing it is called. So how are we going to do? Let us see. Okay. So here we create test cases so that each decision in the code executes with both true and false outcomes. So basically two test cases. So we take that simple example only. So we have exercised the statement coverage in two techniques. Similarly for decision or branch coverage testing, what we do is for true false conditions we will have it. So we use tools as well for this. It's called instrumentation tool where decisions have been taken care. And here also the coverage aspects are done with the help of a percentage, whereas total number of executed decision outcomes have been considered. That means total number of decisions, how many are there against total number of executed decisions. That means suppose we have covered two diamonds and each diamond will have two outcomes, true false, then there are 4 because 2 into total number of decisions, because each decision will have two outcomes, either a true or false. So one diamond if we have exercised or two diamonds with one outcome we have exercised, it means the path is 2, so the coverage is 50%. So this also can be done with the help of a tool. So both are called same basically, branch coverage or decision coverage. So it's a technique similar to statement coverage. So the idea with the decision coverage is to execute every decision, single decision in the code at least twice. It is not once. That you have to remember. Every decision in the code have to be exercised twice. In statement coverage, only once is enough. Here twice because the decision will take 2 paths. That is why we need to have this criteria, very important. So both possible outcomes of the decision, true and false, should be executed in order to reach full decision coverage. By the first glance, statement and decision coverage seem to yield exactly the same test cases, but executing every decision with both the true and false outcomes will result in all statements being executed. So, in order to execute all statements, all outcomes of every decision needs to be executed, that is true and false. So, but there is one case in which statement coverage can be reached without having full decision coverage, and that is with an if statement without an else clause. So, in that case, we will not have false conditions. But that is not a good programming practice uh, to have if something do statement if some condition statement and there is no else. So in this case only one way it is possible, but it is not a good practice to have one if without else. So else have to be there, else do some other statement, some other execution path. So definitely we are going to have a multiple paths for true as well as false. So obviously we still need a second test case with a false outcome to reach the decision coverage. So coverage is measured by dividing the total number executed decision outcomes by the total number of decision times multiplied by 2. So and the tools that are used in this also same tools for monitoring the coverage, where a decision coverage is taken care as well as the statement criteria has been met. So that is with that basically. And further, decision coverage requires two test cases, one for true outcome and for false outcome. For simple decisions, that is decisions with a single condition, decision coverage ensures complete testing and control constructs. For the decision A or B, test cases true false and false false will toggle the decision outcomes between true and false. So we have reached that. However, the effect of B is not tested, right? That is, those test cases cannot distinguish between the decision A or B and the decision A. So the analysis should confirm the degree of structural coverage appropriate to the software level, whatever the level of the software that is. Depending on that, the analysis should confirm basically whether A has an effect or not. For a decision statement, both true and false conditions should be tested, even if the decision statement is of implicit form. If condition is true, then one of two decisions have been covered. To achieve 100% decision coverage, both true and false conditions have to be achieved in two different scenarios, even the statement is implicit form. Okay, so here the same example we see here, statement 1, 2 with condition yes will take into statement 3 and 4, and the condition no will take into statement 5. So two conditions are to be covered, true and false or yes or no. Decision coverage is with the help of a percentage executed decision outcomes. Here only one decision outcome is there, divided by total number of decisions, that is 1 into 2, 2. So there are 2 in the denominator and 2 in the numerator. That will make 100% decision coverage. So that is about the decision coverage. Next one we will see the other technique called data flow testing. Here also the data flow testing uses the control flow graph. Control flow graph is, we know that it's a basic control of the program, how it is going to execute with the structure of the program. So data flow testing uses the control flow graph to explore the unreasonable things that can happen to data. That means basically we use the data in terms of controlling the flow. Consideration of data flow anomalies leads to test path selection strategies that fill the gaps between complete path testing and branch or statement testing. That means we test using the control flow, all the statement, decision and everything. But sometimes what will happen is purely the flow is based on the data for certain cases. So there are gaps by doing that selection criteria with the help of path testing and branch or statement testing. So in that case, data flowing testing is useful. Data flow testing is the name given to a family of test strategies based on selecting paths through the program's control flow in order to explore sequences of events related to the status of data objects. We know that data flow testing is done with all the data flow objects where data is the key here. Data could be a variable. Example, pick enough paths to assure that every data object has been initialized prior to its use. All defined objects have been used at least once. So how data flow testing we can do? Example is that the variables or the data that are used should be initialized because there is a requirement that the initialization function will take care of the global variables. System gets initialized upon power up. So what will happen is the system gets initialized. So all the variables and the data that are part of the initialization function, init function, will get initialized. So how do we do is with the help of data flow, whether that initialization is done for each of the intended data. It could be a variable or anything. So what will happen is that init function, whatever the where 1, where 2, we have initialized to 0. So initialized doesn't mean that it could be 0. It could be any value that is used as a init value and throughout the entire program. So this is very important because the data flow, if instead of 1, if you had put as 0, it could fail because where 3 is being initialized and that initial value in static increment in the other program may use it so that the increment will happen if it is initialized with 1 as 2, 3, 4. If it is initialized with 0, the increment will go wrong. Similarly, if the variable 1 and 2 are initialized to some other value than 0, the program can collapse. That is why it is very important to have data flow testing along with other type of testing techniques. The next one is this is also very important. Whatever the data or the objects that are defined should be used. It's very important because we cannot have a data that is dead. It's called a dead object which is not used. Also called as dead object. So this is very important. We cannot have because unnecessarily it will occupy the memory without the need, and sometimes it may so happen that there are other functions that could use the same name as the one that is there here in the other program, which is unused, will result in some sort of a anomalies in the program. So better to avoid this type of things, and this will be done with the help of data flow testing. And further, the data type objects are defined in the data flow testing. So type D type of data or the objects are of the types having defined, created, and initialized types. K type is killed, undefined, or released ones. Mostly this is used in embedded applications or C++ based applications. U type of data object is used type, so used in a calculation or used in a predicate. An object that is a variable is defined when it appears in a data declaration or it's assigned a new value, file that has been opened is dynamically allocated, etc. So all those are called as an object. So there is a definitely a requirement for this, and against that objective of that particular variable or the object as per the definition we need to test it. So an object is used, it is called as used when it is part of a computation or a predicate. So you can see C or P type. C is for calculation, P is for predicate. A variable is used for a computation when it appears on the right hand side. That means the variable is used uh, when it is used for comparison or assignment, etc. Some sort of a computation. That is called as a C type. Used object data object type. Sometimes even the left hand side in case of array indices also will be used of an assignment statement. Just write one for your understanding. RHS is right hand side. LHS is okay. So accordingly the variables are computed. So variable is used in a predicate when it appears directly in that predicate. That means variable can be used as a predicate by itself. That means the variable can be compared directly, something like if where A is something, then take some conditions or decisions, and that where is getting updated with some sort of a signals or whatever it is. So those are called predicate variables, where there is no assignment or RHS, LHS type of a usages are done with the help of that variables. Okay. So next one is examples of data flow testing data object types. You can see definition, CUs, PUs. As I said, definition is defined, created, initialized. The other one is CUs and PUs. For calculations, we use C type of objects. For predicate, we use P type of objects. This is a small example program. Read XY, Z equals X plus 2 if there is a condition. So. So this is a printf statement. And how are we going to segregate the different types of data objects here? X and Y are defined with the help of read statement. Read function rather. Z is also a defined one. W is another one. Y is another one. C is a computation use because X is used for computation. You can see on the right hand side. Also we have Z. Also we have Y. We have WZ, etc. Because print is used. Print we have supplied as 4 parameters. That's why it is C use. For P use, PC we use the predicate directly, where Z is less than Y is used as a predicate for doing some if condition. That's why it is called as P use variables, data object types. So all these need to be verified in data flow testing. So data are as important as code because having the implementation along with the data is as important to flow the program and define what you consider to be a data flow anomaly. I mean, you understand the program flow and the data that is used in the program, and that definition we need to consider in terms of any anomaly, how it is being used, what against what is being spoken in the requirement. So data flow testing strategies span the gap between all the paths and branch testing. So it is not just enough to have a just branch testing by supplying Z and Y values and make sure that the path 4 is done. 1, 2, 3, 4, 6. One path is here. In this decision testing, what we do is paths 1, 2, 3, 4, and 6 are done. In the other type of decision testing, with the else part executed, what we do is 1, 2, 3, 5, and 6. This path is executed. Still, we would have missed if the variable is been assigned wrongly, or Z is supposed to have X plus 2, and specification says that it should be X minus 2, and we have missed it. So we believe that whatever the statement is available before the decision testing is being tested properly. So it is very important to have a data flow testing also. So how do we do? By having all the paths exercised with the focus on the data. So there is a gap between the path and the branch testing is what data flow testing takes care of. Okay, so we have studied about statement testing, where all the statements have to be executed and invoked, and in branch or decision testing, we have seen every diamonds or the crossing blocks, the conditions or the decisions. Sorry, it's not conditions. Branches will be tested, and data flow testing we do the data or the objects of different types will be tested. And in the next session, we will study about the branch condition testing, branch condition combination testing, modified condition testing, and the last type is LC SAJ testing. And we will touch base on the D1 and NCDC also. Okay. So some of the embedded system testing words we will go through. What we have added today is a branch, condition, decision, data flow. So along with other words, we list out for each session how many embedded system jargons or words we use it. Of course, there is a glossary. We have added some more glossary into Kuro, such as lithometrics, logical test case, low-level tests, master test plan, MIL, model input, mixed signals, model-based development, MBD, output quality, example ISO 8402 standards, quality assurance, quality characteristics. So we will add likewise each session some of the glossaries that we need to understand in embedded system testing. So with that, we'll end this today's session, and the next session we'll continue on the white box testing other techniques.